So we're beginning lesson 4.5, and in lesson 4.5 we are going back to a conversation we had in chapter 2. In chapter 2 we talked about linear functions and what makes a function, and we continued that conversation into chapter 3. So a real simple explanation of a function is that for every time you input a number into the function, you get exactly one answer out. So we don't expect that if I put in 2 that I'm going to get an answer of 1 and 5 at the same time. It's kind of like doing a multiplication problem of 4 times 6. We're expecting the answer to be 24 and not 25 or 23. So each of these math problems we're expecting when you input a number, we get one answer out. So in this lesson what we're going to do is we're going to continue with the idea of looking at functions, but we're also going to be looking at what's called an inverse of a function. And an inverse of a function is basically taking the answer that we got and placing that answer into an inverse function, and that gets us back to the original answer. So if I put in 1, then I'm going to get 2 back. If I put in 5, I get an answer of 4 back, and so on. So an inverse is not a function. For example, if I would get 11 for the 19 and I got 7, that would mean that the inverse is not a function. So not all inverses will actually be functions, and so we have to check to make sure that in terms of the answer we're getting, that it really does produce a function. So here are some mappings, and so what I'd like you to do is I would like you to create the inverse mapping for each of these, and in doing so, which ones are functions. Now in your original copy, this word here said inverses. It's supposed to say the word functions. So which inverse mappings are actual functions, and then circle the examples that work. When you're finished, turn the video back on and we'll continue the conversation. So instead of a mapping, I'm going to write this as a t-chart. So that means if I stick in 11, I'm expecting the answer of 3. If I stick in 13, I'm expecting the answer to be 5, but also the answer could be 6. And if I stick in 15, the answer I'm going to get is 9. This is not a function, because I can stick in 13 and I can get 2 answers back, the 5 or the 6. So hopefully in this first one you did not circle it as a function. If you need to go back and correct the other 2, this would be a good time to turn the video off, make any corrections you need to make, and then turn the video back on when you're ready. So in this one, I'm going to write them as ordered pairs. So if I'm going the other direction, that means if I stick in 9, I'm going to get an answer of 2, because sometimes when we do inverse functions, we're going to graph them. If I stick in 13, I'm expecting the answer to be 3. When I stick in 21, I'm expecting the answer to be 11. And when I stick in 30, I'm expecting the answer to be 13. In this inverse, all of the x values are different, unlike this one here. I had two 13s, and so each x values give me exactly one y answer. So this is an example of a function. And then the last one, I'm going to do it again with a order pairs. So the 15 goes back to the negative 3. But also the 15 could give me an answer of 0. And the 15 could give me an answer of 5. And the 15 could give me an answer of 11. So the 15 can actually give me 4 different answers. So this is not an example of a function. Only the second one is. So in terms of the language in mathematics to communicate a function versus an inverse function, you actually were introduced to this idea in geometry. You were doing trig problems, and so on your calculator, for example, you would use a tangent key. But sometimes you would use inverse tangent. That's when you were trying to solve for an angle measurement. You did the same thing with sine and cosine, that there was, if you look at your calculator, you'll see this -1, and it's not read tangent to -1, it's actually read inverse tangent. It's basically the undoing of a function, so in terms of tangent function, or sine or cosine, we're doing inverse sine or inverse cosine. So in function notation, we also use that idea of a -1, and so we read this as the function of x and call this the inverse function of x, not f of x to -1. So what we're going to do here again is the inverse, so that means that when I put in the value of 0, I'm getting back an answer of 5. So that would be the first answer in this table. So if you complete the table, as the direction asks you to do, and then based on the inverse table, can you come up with the equation for this table? And again, when you're finished, turn the video back on. So I've already written the inverse table out, so hopefully your order pairs match my table. So in establishing the equation, we look for the 0 value for x, so that means the b value in our equation is 5. This is the place where the graph is intersecting the y-axis. For slope, we're looking at the change in the inverse side of it and the change in the x side. So as I go from 5 to 8, that's an increase of 3 as x increases by 1. So the slope is defined as the change in the y value over the change in the x value. So the change in the y value is 3. The change in the x value is 1. So the slope is 3. See whether this is a linear function or not. In terms of the equation, if I go from 8 to 11, that increase is also 3, as the increase in the x value was 1. 11 to 14 is also an increase of 3, as x increased by 1. And same thing for the last one. As the inverse answer, or sometimes called the y side of the table, increases by 3, the x side of the table increases by 1. So in all 4 problems, the slope value is 3 over 1, or simply 3. Reason why I'm talking about both sides of the table, which we don't spend as much time as we probably should, is because generally when we create the x side, we make the numbers consecutive, and so that means the slope is just simply whatever this number is here. In the next problem, which you'll need to work on, and if you notice on both sides of the table, when you're writing the inverse, neither side is increasing by 1s. So to establish the slope, you will need to look at both values and see what that common slope is. So, for example, you could have 3 over 1. You might actually have a 6 over 2, for example. So, for example, maybe I would have, if I eliminated this pair here, and I would have gone from 0 to 2 and 5 to 11, that would have been an increase of 6. And x would have increased from 0 to 2 by 2, so the fraction could have been 6 halves. You could have had a fraction 9 thirds. So you will find that in the next problem that all the slopes may not be the same fraction, but hopefully they all simplify to the same slope if we're talking about a linear equation. The next set of problems, and actually this is the last set of problems we covered in class on Thursday, is our graphs, and we're looking at trying to draw the inverse graph for the given equation or given graph. And there's, I think, 5 of those altogether. So when you get to this problem here, you're done. We will continue here on Monday next week. So for the inverse, we're basically taking each of the ordered pairs, and like I demonstrated on the first page, we're going to take each of the ordered pairs and we're going to reverse the number. So instead of plotting 2, 9, for example, the inverse would be 9, 2. If it's 3, 13, then the inverse point would be 13, 3. So on this problem here, this first one, this point here is at 3, 3. So x value is first, y value is second. So the inverse of that would also be 3, 3. So these two graphs are going to intersect at 3, 3. This point here is at 2, 1. So that means the inverse point would be at 1, 2. The The next point is at 1, -1. So its inverse point would be at -1, 1. Next one's at 0, -3. So its inverse point would be at -3, 0. And the last point is at -1, -5. So its inverse point's at 5, -1. So based on the points that are graphed here, is the inverse also a function? And so what we try to look at is, based on the points, do the points seem to take on a shape? So we're looking at, is a shape another line? Is it another parabola? Is it a square root graph? Is it a combination of two graphs, for example? So what we're looking at is these points here. If I would go ahead and use a straight line tool, it appears all of these points are falling on a straight line. Now we could check that idea, and I would encourage you to consider doing that. You could check that idea by just simply choosing some other points and see if it continues. So for example, we have a point here at, looks like about 1 and maybe 1/4, 1 1/2, somewhere in there, 0. So that would be 0, like 1 1/4, 1 1/2 right there. If I choose this point right here, for example, this is at 4, 4, 5, over 4 up 5. So if I go over 5 up 4, the point's right there. I could choose this one. It was like right here. It was like about 5, 7. So if I go over 7 up 5, it's right there. So by checking other points, it appears that the inverse is truly another line, and all the answers we're coming up with is exactly one point for each x value. So this would be definitely a function. So you have 4 more to do, and I left these for your class to do as part of their in-class work to homework. So I'll go ahead and finish off the other line, the 2 parabolas, and this is called a cubic function. This is created by the equation y equals x cubed, or x to the 3rd power. So when you're finished with these problems, that was the only additional homework that was given to them if they didn't get done in class. But their main focus, obviously, is to get those 2 decimals activities that were assigned earlier completed by Sunday. So if you have any questions, let me know.